When we talk about the different types of sedimentary rocks, we often treat each one like it's its own unique form of substance or matter. Sandstone, siltstone, coal. But this is a gross oversimplification of things. Sedimentary rocks are actually solid mixtures. A solid mixture consists of two or more different types of solid matter, which are chemically distinct from each other. In this case, the different types of matter are minerals, which occur in various forms. In the case of terrigenous rocks, some of the minerals occur in lithic fragments, or clasts derived from pre-existing rocks. Lithic fragments are also solid mixtures. Other minerals occur as homogeneous mineral grains and cements, each one composed of a single type of mineral. To determine the origin of a terrigenous sedimentary rock, a geologist will study its grains and cements with two goals in mind. First and foremost, the geologist will work to identify the minerals that make up the lithic fragments and mineral grains. The composition of the lithic fragments and mineral grains tell us about the source rock, the bedrock that produced the sediment. The source rock is the rock which was weathered and eroded to produce the sediment that became the terrigenous sedimentary rock. Source rocks come in many varieties. Some source rocks are igneous. Other source rocks are sedimentary and metamorphic. In any case, the source rock leaves a mineralogical fingerprint on the lithic fragments and mineral grains of the sediment that it comes from it. In this context, geologists can go from a terrigenous sedimentary rock or lithogenous sediment sample backward to the source rock that produced it by studying the mineralogical composition of its lithic fragments and grains. We refer to the origin of a sediment sample or a sedimentary rock as its provenance. Besides provenance, a geologist will also study the minerals in a terrigenous rock so they can better understand its history of diagenesis. When did it undergo lithification? How deep was it buried? How hot did it get? Is there evidence of burial compaction? What sorts of cements are present between the grains? And how exactly did they form? What can they tell us about the depositional environment? Are the pore spaces completely filled by cement? Or is the rock permeable? Can fluid flow between the grains? Is there evidence of dissolution, recrystallization, or replacement of minerals over time? The answers to these questions can help a geologist determine the depositional environment in which a terrigenous rock formed. They can also help the geologist to determine its tectonic history of burial, subsidence, and uplift. Not to mention, observations of the grains and cements in a sedimentary rock can also be used to assess its potential as a hydrocarbon reservoir or other component of natural resource geology. The first step in studying the provenance and diagenesis of a sedimentary rock is to prepare the rock as a petrographic thin section. A petrographic thin section is a slice of rock that is so thin that light can shine through it. Generally speaking, this means that a thin section is about 30 micrometers thick. A thin section is created using a special saw for cutting rocks, along with various other pieces of equipment. The saw is used to cut a piece of rock down into a rectangular cuboid, usually around 25 millimeters wide by 45 millimeters long and 5 millimeters deep or so. We refer to the rectangular cuboid as a thick section. The rest of the material is usually set aside and saved for other projects. The next piece of equipment that is used is called a grinding and polishing wheel that is affixed with grip paper or some other coarse material. This wheel is used to polish one surface of the thick section so that it becomes very smooth. The thick section is then glued to a glass slide with an adhesive glue-like substance called epoxy. To complete the thin section, so light can pass through the rock, material must be removed from the thick section, and it must be trimmed down. This is accomplished by again using a rock saw to remove the bulk of material, and then using grit and a polishing wheel to slowly remove material from the surface of the thick section. It can take quite a while to polish a rock down to 30 micrometers, but in the end, light should pass right through it. We study petrographic thin sections like these with special geologic microscopes called petrographic microscopes. Petrographic microscopes have all of the traditional features of compound transmitted light microscopes, as well as a few additional features that are necessary for mineral identification and mineralogical analysis. Like all compound microscopes, a petrographic microscope has a stage for holding the thin section, which is illuminated from a light source located below it. The user can change the amount of light that passes through the thin section by adjusting an aperture located beneath the stage. The user can also adjust the level of the stage and the focus of the microscope with two adjustment knobs located on the side of the microscope. Magnification of the thin section is achieved with two lenses, a large objective lens located right above the stage, as well as ocular lenses located in the eyepieces. The user can change the magnification by swapping the objective lens, and the total magnification is the product of the objective and ocular lenses being used. In addition to these standard features of all compound microscopes, petrographic microscopes have several special parts. Rather than fixed stages, the stages on petrographic microscopes rotate around the fixed axis of the light source, aperture, and objective lenses. These rotating stages turn clockwise and counterclockwise, and it's up to the user to keep the thin section slide in place with their hands. The other distinguishing aspect of petrographic microscopes is that they have two filters of light. One filter, the polarizing filter, is located between the light source and stage. This filter allows some, but not all of the wavelengths of light to pass through it. The other filter is called the analysis filter, and it is located above the stage between the objective and ocular lenses. It also filters some, but not all of the wavelengths of light that pass through it. However, unlike the polarizing filter, the analyzing filter is on a track, so it can be pushed in and pulled out as needed by the person using the microscope. In order to understand why petrographic microscopes have rotating stages and two filters, and how they work, we need to explore how light travels through the microscope, and more importantly, how light travels through the minerals in the thin section. Light consists of electromagnetic waves. These waves vibrate and oscillate as they travel across any distance. When these waves pass from one medium to another, like air to water, their speed changes. They either start moving faster or slower. As a result, the path of light bends in one direction or another. If light passes from a slow medium to a fast medium, the waves bend away from the axis that is normal to the boundary between the two media. The same principle applies to minerals. The speed and trajectory of light that travels through a mineral depends on its composition, density, and the orientation of its crystal. Importantly, these relationships affect the appearance of minerals under the microscope, and so we can use the appearance of minerals in thin sections to help us identify them. In order to do this, the microscope filters unpolarized light, blocks certain waves, and lets polarized light pass through it. This means that the filter only allows light waves vibrating in one plane to pass through it. Plain light, consisting of wavelengths of many varieties, becomes polarized light, with the wave oscillating in only one plane. The analyzing filter, located above the thin section, does the same thing as the polarizing filter. However, it is mounted perpendicular to the polarizing filter. As a result, Light waves can only pass through both filters if they are vibrating at 90 degrees with respect to each other. Therefore, light only passes through both filters if there is refraction of the waves as they pass through a mineral. If there is no refraction between the filters, or if there is no thin section between them at all, then no light is getting through both filters and the view in the microscope appears black. However, minerals refract light. So if minerals in a thin section are present between the two filters, the light will be refracted and the minerals will be visible under the scope. For this reason, the filters allow us to recognize minerals under the microscope. Because the refraction and vibration of light depends in part on the orientation of a mineral crystal, we can use plane polarized light, cross polarized light, and the rotating stage of the petrographic microscope to observe how the appearance of a mineral changes as its crystal is reoriented with respect to the plane of light. This all sounds very complicated, and it can be quite difficult. One must always be mindful of how light is being filtered in a petrographic microscope. If both filters are being used, then we say that the light that reaches the eye is cross-polarized, because the directions of light being filtered are crossed. Conversely, if light is only being filtered by the lower polarizing filter, then we say that the light is plane polarized light. Thin sections look different under plane and cross-polarized light. Under plane polarized light, some minerals are transparent and appear white. Other minerals block light from reaching the eyepiece and are black. And other minerals have entirely distinct colors. Under cross-polarized light, the same minerals can have very different colors. But always remember, we're simply looking at the appearance of minerals in cements and grains. Some minerals look similar while others are strikingly different. But each one has a set of characteristics under cross-polarized and plane polarized light, which we can use to identify it. So what are the characteristics of minerals in thin sections that help us to identify them? Well, two of the most obvious characteristics are opacity and color. Again, under plane polarized light, some minerals are transparent and appear white or slightly cloudy. Other minerals block light from reaching the eyepiece and appear dark. Here, you can see an iron oxide called magnetite. Iron oxide and iron sulfide minerals like magnetite and pyrite, along with organic matter and other materials containing heavy metals, all tend to appear black or very dark brown in petrographic thin sections. This is because they have high opacity. In other words, they are opaque and block light from shining through the thin section. That said, many of the most common minerals in sedimentary geology are translucent in plane polarized light, including quartz, feldspar, calcite, micas, and clays. These minerals are often colorless and appear clear and white. In some cases, however, they are cloudy and have distinct hues and tints. Micas, like these shown here, are sometimes green or brown. Yellow and blue minerals are also possible. Here, you can see a crystal of kyanite as the stage is rotated. But beware, color is not straightforward. The color of the kyanite crystal changes from blue to purple and pink as the stage is rotated. We refer to this phenomenon as pleochroism. Pleochroism occurs in a mineral under plane polarized light when its color depends on the orientation of the crystal. As the orientation changes with respect to incoming light, the mineral absorbs different wavelengths. As a result, some minerals, like kyanite, are pleochroic and have multiple colors under plane polarized light. Pleochroism is one of the reasons why the stage rotates. It allows for examination of color in minerals positioned at various angles to the plane of incoming polarized light. It's also important to point out that the minerals that have colors in hand specimens may not have any colors in thin section whatsoever. Purple quartz, for instance, appears completely colorless beneath the microscope. It's also worth pointing out that some of the colors you may see in a microscope may not actually be minerals at all. Here, the blue is a dye that was injected into the rock as it was prepared as a petrographic thin section. This dye fills the pore spaces between the grains in a permeable rock, helping in the analysis of its porosity. Beyond this porosity, dye, and pleochroism, a final concern about color deals with the type of light. Is the thin section being analyzed with plane polarized or cross polarized light? Minerals that appear one color under plane polarized light will usually have an entirely different color under cross polarized light. Quartz and feldspar, for example, are white under plane polarized light, but they appear black, gray, and white under cross polarized light, depending on the orientations of their crystals. We refer to these colors under cross polarized light as the birefringence colors of the minerals. If a mineral has low birefringence, then it is usually some shade of gray. Other minerals have high birefringence and come in a spectacular array of colors. However, again, the color of a mineral under cross-polarized light depends on the orientation of the crystal. As the stage is rotated, the color can change. So, each mineral actually has a range of birefringence colors that it can possibly be. The birefringence color of a mineral depends on how the mineral distorts and refracts light as it passes through it. Here, you can see a feldspar grain as the stage is rotated. It goes from white to gray to black. If a mineral becomes black under cross-polarized light as the stage is rotated, we say that the mineral has gone to extinction. Extinction happens when a mineral is oriented in such a way that it does not influence the path of light. Because it does not refract light, no light waves are able to pass through both filters, and the thin section appears black at that point. Black is the absence of light. Feldspar and quartz both exhibit this extinction behavior. But this is not true for all minerals. Many minerals do not go to extinction. Therefore, extinction is a good characteristic that helps to identify some minerals. There are various other observations that you can make to help you identify a mineral with petrographic analysis. Another important characteristic of minerals in thin section is form. Is the mineral a grain or is it a cement? Is it a mineral grain or is it a lithic fragment? Certain minerals are more likely to be one thing than the other. Here, you can see a poorly sorted sandstone cemented by calcite under cross-polarized light. The black and white and gray clasts are quartz mineral grains. They're surrounded by a pink cement made of calcite. If you find calcite in sandstone, it is most likely in the form of cement, not clasts. Quartz can also occur as a cement. Unlike calcite cement, quartz cement is white, black, and gray under cross-polarized light. Here, quartz cement is filling pore space between quartz mineral grains. Another obvious characteristic of grains is their shape. Grains come in all shapes and sizes, but some are more likely to appear as one shape than another. Micas, for example, tend to have long, thin grains. Here, you can see an aqua blue grain of muscovite. You can tell it's a mica because, like other micas, this mineral is a sheet silicate, meaning it consists of many thin sheets. These sheets, or layers, are often clearly visible in thin sections. The fracture spaces between them are sometimes filled by cement. In this case, some of the spaces are filled by calcite. This leads us to cleavage. Cleavage is the tendency for grains to split and fracture along structural planes determined by the crystal lattice structure. Think of cleavage like taking an axe to a mineral. You would most commonly cut the mineral in a certain way, given its crystal lattice structure. In the case of micas, like muscovite and biotite, you would probably use the axe to separate the different layers. It has one direction of cleavage. But there are some minerals, like quartz, with no distinct planes of cleavage. And there are others with multiple directions of cleavage. Feldspars, like orthoclase and plagioclase, have 2 directions of cleavage. Calcite has 3. In any case, this characteristic of minerals in thin sections is important because they often have very distinctive cleavage patterns. Quartz grains, like these, don't have any lines of cleavage. You can only see microcracks and fractures caused by stresses created by sediment loading and burial compaction during diagenesis. These fractures are completely distinct from real lines of cleavage. Feldspars can look very similar to quartz, but they have very clear lines of cleavage. Here, you can see an albite anorthite feldspar grain with clear parallel lines of cleavage. The grain also illustrates another interesting feature, polysynthetic twinning, with straight twin boundaries and concentric zones that reflect changes in composition during crystal growth. Crystal twinning is a phenomenon where 2 separate crystals share some of the same crystal lattice structure. In other words, the 2 crystals share a surface and appear to grow into or out of a twin plane. The twinning is associated with straight twin boundaries and concentric zones related to changes in composition that occurred during crystal growth. Twin crystals are common among feldspar minerals, and it is most easy to observe them under cross-polarized light. The twinned crystals will go to extinction at 180 degrees with respect to each other. Twinning is an especially common feature of plagioclase feldspars, like albite and anthrite. As a result, these minerals tend to look zebra-like. They have a black and white striped appearance. Of course, not all grains consist of just one mineral. Lithic fragments are clasts derived from weathering and erosion of pre-existing rocks. Lithic fragments, such as these, generally consist of multiple minerals. You can recognize lithic fragments because they contain crystals of various shapes and colors. Crystals can be elongate, equant, or shaped like many needles. Here, you can see calcite cement. It consists of fibrous crystals arranged radially around a center point. A final characteristic of minerals under the microscope is relief. Relief refers to how strongly and distinctly you can see the boundaries around minerals, grains, and cements. This crystal is titanite, a rare calcium titanium neosilicate mineral. It has very high relief. As a result, it appears to jump out of the background. In general, dense materials made of heavy elements like titanium or iron tend to have high relief. As we conclude our introduction to petrography, I'd like to leave you with a few suggestions on how to best proceed. In my opinion, petrography is one of the most challenging aspects of sedimentology and stratigraphy. It takes time and experience to learn how to differentiate between mineral grains, lithic fragments, and cements. And it takes even longer to develop the skills to distinguish between many types of grains simply by appearance. The best advice I can give you is this: focus on describing thin sections, rather than identifying minerals. There are many mineralogical textbooks that provide keys that can help you identify just about any mineral you find in thin section. But to use these keys, you have to be able to describe minerals in terms of color, opacity, pleochroism, birefringence, extinction, twinning, cleavage, and relief. Describing these things are the first step. In the future, I suggest you do the following. Start big. Look at the whole sedimentary layer or hand sample before you look at a thin section. When you do begin to look at the thin section, start at a low magnification with plain polarized light. Take notes on the grain's colors, opacity, and relief. Once you have a lay of the land, then you should zoom in on the grains and cement and collect more information. You can also then, at that point, switch to cross-polarized light and look at birefringence and extinction. Only after you have all of these things can you start to try and figure out what minerals are present. One of the most common goals in petrography is to determine the percentages of rock that are certain minerals. You should wait to tackle this question until you know exactly what minerals are present in your thin section. Once you do, you can use a random sampling method like point counting to get a sense of how much of each mineral is present and what percentage of the rock it represents. From there, you can finally move on to questions about provenance, diagenesis, and depositional environments. Whatever you do, don't give up. Petrography is a skill like any other, so practice, practice, practice. It's the only way to get to Carnegie Hall.